You have watched a lot of videos about rocks. Here's the final one to summarize some of the key points. Take a look at this picture here. I'm going to give you a question and an answer later on. The question is, describe how these rocks formed and how they are related to each other, and the arrow is a hint. So let's talk about the three rock types in terms of the key features that you should make sure you understand. First of all, igneous rocks form from magma, and they cool and they crystallize to form solid rocks, just like water freezes and forms ice. Rocks that form and cool inside the earth are called plutonic or intrusive, and rocks that form on the surface, typically from volcanoes, are volcanic or extrusive. This cartoon shows those two different realms: the extrusive realm, which is volcanic, and the intrusive realm, which is below the surface. So here we have a magma chamber. It's feeding the volcano, so the magma is going all the way to the surface to make volcanic rocks. But in many cases, this magma stalls and does not make it to the surface, cools and crystallizes over millions of years below the surface, and we end up with plutonic igneous rocks. Igneous rocks are classified on the basis of two features: texture and composition. The texture has to do with the size of the crystals, and remember that this is directly related to the rate of cooling. Slow cooling forms large crystals, such as shown here in this rock. Fast cooling produces microscopic crystals. They're there, but they're very difficult to see without a microscope. And extremely fast cooling forms no crystals. It forms a glass, such as obsidian. The other way igneous rocks are classified is on the basis of composition. And the two major groups of composition that we've learned about are the dark rocks that are composed of dark silicate minerals, and these we know as mafic, or the light rocks that are composed of light silicate minerals, and these are known as felsic. So the key to understanding how to classify a rock is to be able to figure out its composition and its texture. So here's an igneous rock chart that shows you composition across the top and texture along the side. Let's take a look at two of the rocks that you had in your rock kit, number I-10 and I-17. Let's start with I-10. I know from the light color that this is a felsic rock, so I'm going to circle the felsic column. I also know, because I've looked at it carefully, that it's a fine-grained texture, so I'm going to circle the fine-grained row. We look at where the column and row intersect, and we have a rhyolite. So that's the name of this rock. The rock next to it, I-17, has about 50-50 dark and light minerals, so we're going to call that intermediate in composition. It's a coarse-grained rock. We can see the actual minerals, so I'm going to circle coarse-grained. And where those two intersect tell us that we have diorite. So that's how you use this igneous classification chart. Moving on to sedimentary rocks. Before we get to sedimentary rocks, remember we have to talk about sediments. Sediments are the product of weathering, and there are two kinds of weathering. Mechanical weathering is the actual physical breaking apart of rocks into smaller pieces. Two important types of physical weathering include frost wedging, in which water gets into cracks of rocks, and in the winter it freezes and ice expands and breaks the rocks apart. Another type of mechanical weathering is called unloading, and this happens when rocks come to the surface that formed deep below the surface, and the pressure is sort of released and they start to peel away, almost like the outer skin of an onion. The other type of weathering is chemical weathering, and this typically involves water. Chemical weathering involves some sort of change in the chemistry of the rock. Oxidation or rusting is what turns rocks red, because the iron has oxidized in the minerals. Dissolution by acids or acidic rainwater can also decompose rocks, such as has been done to this statue here. The result of chemical weathering is ions in solution and clay minerals. Sedimentary rocks fall into two categories, detrital and chemical, and these are directly related to the type of weathering products. Mechanical weathering gives us detrital sedimentary rocks, and chemical weathering gives us chemical sedimentary rocks. Let's look at the group on the left first. Detrital sedimentary rocks are defined on the basis of how big the pieces are in the rock. Remember, the weathering gave us pieces. These three examples here are showing how we name rocks based on those sizes. Conglomerates have gravel-sized pieces, sandstones have sand-sized pieces, and this shale, which has some fossils in it, has clay-sized pieces. Remember that the sediment is compacted and buried and lithified. The compaction squeezes out the water and the air, and then a natural cement comes in and cements those grains together. If that didn't happen, then the grains would simply be loose and fall apart when this came back to the surface. So we have muds that become shale, sands that become sandstone, and gravels that become conglomerate. And remember that sedimentary rocks tell us a lot about the environment in which they formed. The other type of rocks are the chemical sedimentary rocks. And these are not based on the size of the grains, but these are based on their chemical composition. What are they made of? Here we have a fossil-rich limestone, and limestone is made of calcite. In fact, there's a lot of different kinds of limestones. Down here we have rock salt, which is made of sodium chloride, and bituminous coal, which is made of altered plant fragments. So the classification of these two groups of sedimentary rocks is quite different. How do chemical sedimentary rocks form? They tend to form by precipitating out of solution. For example, if you have an undersaturated solution of water, let's say you have iced tea and you put some sugar in it and the sugar dissolves, then you could certainly dissolve more sugar in it because your iced tea is undersaturated. Eventually you would get to a point of putting sugar in your iced tea where it could not hold any more. And if you continued to put sugar in, you would actually eventually grow more sugar crystals. That would be a supersaturated solution. So if the ocean water is supersaturated, it cannot hold more of that dissolved material, and it might actually grow. And this is one way that limestone forms. Here's another shot of some limestone and some limestone shells. So organisms make limestone. This is showing a little cartoon of an oyster's life. And oysters, just like clams and other shellfish, are not born with shells. They're born as these little polyps and larvae that eventually take calcium carbonate out of the water, the ions, and they build their shell. They create it as they grow. And as they get larger and larger, the shell gets larger. So they precipitate it out of solution. It's dissolved and they create their shells. So it can happen biologically, or it can happen without the help of biological organisms. Another way that chemical sedimentary rocks can form is from evaporation. Let's move on to metamorphic rocks. There are two main kinds of metamorphic rocks that I want you to understand. The first one is most common. It's called regional metamorphism, and it affects large regions, in particular large mountain belts. And it occurs when plates are converging. Now we're just starting to learn about plate tectonics, but when two plates merge together, there's a lot of pressure going on. And as you can see in this cartoon here, there's a lot of things that are being pushed together. And that pressure is going to change the rocks. Here's another cartoon showing how mountain building is occurring. And this UHP means high pressure rocks. You don't have to worry about that. But the point is, under these mountain belts, these collision belts, we often get regional metamorphism. Over a large area, we create new rocks. This is also how we create foliation in rocks. So this is a granite that is not foliated. It's an igneous rock, and it has a uniform distribution of minerals as shown here. There's no preferred orientation. In this particular case, the stress that was created by the mountain building event comes in from the left and the right, and as these new minerals grow, remember the new minerals recrystallize, they grow perpendicular to that stress direction because they wouldn't want to grow parallel to it. That would be too difficult. And so they tend to grow in a perpendicular direction. And the felsic and the mafic minerals also tend to separate out to create bands of dark and light. So foliation is an important feature in metamorphic rocks, although not all metamorphic rocks have foliation. The second type of important metamorphism is contact metamorphism, or sometimes called thermal metamorphism, and this occurs along the edges of an intrusion. Here we have magma intruding some rocks, and these rocks happen to be sedimentary, sandstone shale, limestone shale, but along the close region near the intrusion, they have been metamorphosed into metamorphic rocks. Here we have a quartzite, a hornfels, a marble, and a hornfels. Those are all metamorphic rocks. An analogy to this is how there's more and more heat necessary to go from clay to porcelain. So if you know anything about how porcelain is made, at a low amount of temperature, clay becomes a brick. At higher temperature, it can become pottery, and even higher, it becomes porcelain. So this is sort of analogous to the different grades of metamorphism. Low-grade metamorphism means things have only been exposed to a little bit of heat and pressure. And as you go higher and higher, they become higher grade metamorphic rocks. Remember, there's no melting when it comes to metamorphism. This is showing mineral B replacing mineral A, molecule by molecule. It moves in and it makes its new mineral phase at the expense of phase A. Maybe by the end there's little remnants of mineral A, but there's no melting when it comes to metamorphic processes. This is a pressure temperature diagram that shows the surface basically right here, increasing temperature across the top, increasing pressure below, and it shows where various types of metamorphic conditions are. So we have low temperature and low pressure in this corner, high temperature and high pressure down here, and eventually down here we would have melting. But we do have some rocks that are high temperature and low pressure, and those are common in the contact metamorphism realm. We have this large swath here that's common in the mountain belt or regional metamorphism realm. And then we have these low temperature, high pressure ones that are common in subduction zones. So we're back to this picture. So what kind of rocks do we have here? Well, a limestone is a chemical sedimentary rock. And you can see little organisms in here that are fossils. And so those fossils built their shells by precipitating calcite out of solution. And then the muddy matrix that's holding them together is calcite that precipitated out of seawater. Over here we have a marble, and that is a metamorphic rock, but it's a non-foliated metamorphic rock. And to get from a limestone to a marble, this rock had to undergo heat, pressure, and chemically active fluids, or metamorphism, perhaps by being buried to a certain depth. Finally, let's get to the rock cycle. I've already talked about the rock cycle, but now I want to talk about some shortcuts. We've talked about how igneous rocks become sediments by being weathered, transported, and deposited. But sedimentary rocks can also go directly to sediments if they're uplifted and then undergo the same process of being weathered and transported. Similarly, metamorphic rocks can go directly to sediments, so we don't have to go directly around this entire circle. Another shortcut is this. Igneous rocks can be directly metamorphosed through metamorphism. They don't have to be brought to the surface and weathered into sediments. Even metamorphic rocks can be brought back down further than where they originally formed and become metamorphosed to a different grade. There are some shortcuts that don't work very well. For example, you can't take a sedimentary rock and make it become igneous. That just doesn't work. You have to make magma first. All right, that was your review. Next up is plate tectonics.